Alright, so today we're going to talk about two different ways to look at reaction rates. We're going to look at the change in concentration over time, and then we're going to learn how to write a rate law and look at experimental data. So that sounds like fun, right? So, like I said, we can look at the change in concentration over time of a reactant or product, and then you can use a mole ratio to figure out the rest, like in the POGL. Or we can look at the overall reaction, and we can get some experimental data for that. So this is what you had done on Friday without me. And so notice here that you have a negative sign for the change in concentration for reactants, and that's just because the graph of that reactant is going to have a negative slope, right? So if we have a reaction, the reactant's going to look something like that. And so kind of decrease, it'll have a negative sign. And then the products are going to come up, so we don't need a negative sign because it will have a positive rate of change. And this is nothing but a rate of change. Don't let those triangles freak you out. It just means change, okay? There's other scarier things to worry about later. So to me, what this is showing those mole ratios, where we have those coefficients. You know how I took the mole ratios? Sometimes people will just make a fraction and be 2 divided by 4, but I would rather make a mole ratio. This looks really scary, but it's not a big deal. It's just your mole ratios to say that, you know, if this is 2 and that's 4, then I'm going to be making twice as much of these. 2 over 4, or 4 over 2 in that case. No worries. Instantaneous rate change is equal to the slope of a line tangent, and a line that is tangent will touch the line but not intersect it. So that's just what tangent means. I know, did y'all talk about that in like algebra 2, like your little circles? And well, anyway, so if I were given the slope of this line, the rate of change of that line, that would be the rate of production of this product at that point in time. So if this was 30 seconds, then I would know the change or the rate of production for this product would be the slope of that line at that point. I don't see a whole lot of this in the AP exam stuff. They're going to ask more questions about what's at the end of the PowerPoint, but that is a thing, and so I don't want to tell you about it. Here are a couple things I want you to be able to look at. When it decreases like that, then you know that's a reactant. You should just be able to do that at this point. Then I can also tell here that twice as much NO is getting made as O2, or more of it, so I can tell that the coefficient of the NO is greater than the coefficient of the O2. How's that? That's not the worst thing. Y'all still okay? Cool. Here's some pictures with circles. This comes up a lot, I'm not going to lie to you. But don't let this be the reason you fail the AP exam, count circles, okay? So if I start with 15 particles of AB, which is my reactant, after 60 seconds, I basically have 5 particles of AB, 5 of A2, and 5 of B2. So if I wanted to find the rate of change for any of those, that's just going to be the change in concentration divided by the change in time. So for A2, I would just say 5 minus 0, so final minus initial, look, final minus initial, 5 minus 0, which is 5. And then it went over 60 seconds, so 5 over 60 is, that would be my numbers, and I would just 5. So it's not a big deal, okay? That's going to be a positive, so I don't need a negative number in front of it. It just looks really scary when you start to write it down, but it's no big deal. This is what I just told you. 5 minus 0 over 60 seconds, and 5 over 60 yields 0.0833. Now, listen, if I have the rate of change for A2 over 60 seconds of this, if the coefficient for AB is 2 instead of 1, then the rate of loss of that reactant should be twice as much. And look, 8 times 2 is 16, and it is. That's all this is showing. You don't even need to do this math at one time, and then you can use the mole ratio to get the other rate. And so, obviously, B2 is going to be the same as well. You good? Great. Okay, so look, what I've done here, basically today I'm going to tell you about 2 different ways to do kinetics. And then tomorrow I'm going to tell you 2 other ways. Or it might be split over another day. But it's fine when you're talking about one way. And then you start mixing them all together. And what happened to me when I was trying to learn this in a college setting is they just went straight through them. They didn't do anything but read the slides, and I was like, what? And I didn't understand. Like, I was completely lost. I have never been so lost in my life, to be honest with you. And so what I had to do when I taught it to myself again and I actually understood it is I had to be like, okay, self, this is one way, and you do this one way. And this is another way, and it's separate. So what you have to do is you kind of have to look at it and say, well, what way am I using? And so if they give you a change of concentration and a change of time, it's just this, change of concentration, change of time. That is one way. A completely separate way I'm about to show you. This is not anything related to what you just did. So the separate way is here. Now let's go to that slide. All right, now this looks scary. It doesn't at all, but it's not a big deal. All right, so let's talk about this. The rate of reaction is equal to this K. This is a constant, and there's other K's for other things, but this K is a constant. And notice in this rate law, I have A and B. Those are my reactants. Rate laws for kinetics never contain products. Now, why am I saying that? And I'm like being all slow about it. Like, why am I taking the time to do that? Now, take your yellow formula sheet. Let me explain what we're about to do. See where it says equilibrium and then kinetics? We're about, this unit is, I'm going to teach you an introduction to equilibrium and kinetics. So just look at all those formulas there. Now, the fun part is, if you look at equilibrium, you see how equilibrium's formula has a C and a D in it? Yeah. Equilibrium, like it's going to be fine, I'm teaching today, it's going to be fine, I'm teaching tomorrow. Each day is fine. But then when we get to equilibrium, they actually do take into account products. Kinetics doesn't. And there's no rate law in there for kinetics. Look under kinetics, it doesn't have this. So you're going to have to just know this. Isn't that fun? I'm so excited. So what I was saying was, there's will come to Jesus meeting. There's a reactant, and notice how there's no products in this rate law. Now, in case you missed it, these little brackets are molarity, they're concentration. So the concentration of A raised to some power times the concentration of B raised to some power. And this has to be determined experimentally. Do not get in there and think, look, let me show you something. Like if this is a 2 and this is a 3, it is not this. No, these have to be determined experimentally. The rate law has nothing to do with the Balanced equation. So again, only reactants, and the rate law has nothing to do with the Balanced equation. Get to equilibrium, that goes out the window. But for this, that's how to do. So how do you feel so far? I already showed you this, but this is just, now notice that I'll go ahead and tell you about a trick that I try to use on the AP exam. Let's say that this reaction is happening at 100 degrees Celsius. If I change it to 110 degrees Celsius, if K is just a number, okay? If K was 2, and then it goes to 120 degrees Celsius, K ain't 2 anymore. K is temperature dependent. And so I have a little song for you I made up. You ready? Have you heard like the K Jewelers song? How does it go? Every kiss begins with K. Yes, you heard? Okay. So here's how to remember this. You can close the door, Christian. I'm sure I'm not gonna mention any names. That is, but it goes. Only temperature changes K. So K is a constant, but if you change the temperature, it changes K. I want you to hear my voice singing. It's kind of like with average kinetic energy was temperature, and then like they kept the temperature same, and then they changed stuff, and you had to know that it was the same. You know what I'm talking about. So this is a trick that I try to use with that. So even if you can't do math, if you can remember only temperature changes K, like hopefully you'll be okay on that one question. All right, so reactant orders can be 0, first, or second order. Now, when you go to do your homework, I try to pick the easiest questions possible. If you get into your homework, you have the answer keys. If something's half order, whatever, just go with it. Don't worry about it. The stuff that you actually have to do for this class is not that bad, and it kind of comes out even, and everything's cool. Okay, so and this is what's written on the learning objectives for this class: 0, first, or second. It can be other than that, but we're not doing that. We don't have to. So if you get to doing your homework and you're like a little bit lost, don't worry about it. And here for your test and for the AP exam is 0, 1, and 2. All right. So again, these reaction orders are these exponents. These have to be determined experimentally. They are not the coefficients in the bounce equation. They have nothing to do with the bounce equation. Okay. All right. Only found through experimental data. You have to do an experiment. Not a big deal now, but it'll be a big deal later. All right, so let's talk about math because math is fun. For today, I'm just going to make K2. Y'all have to understand that K can be 7.5, K can be 0.0004. But I'm just going to make it 2 because I like to multiply by 2 because I'm, a simpleton. So K is 2 for this reaction. And we're keeping the temperature the same, so it's going to be the same. Now, if the initial concentration, now you got to remember we're talking about like, a reaction of some kind. Ooh, I messed up. A has to be a reactant. So if A plus B gives you AB, do you see why I'm like backed up and punted? Because the thing is, like I wrote AB gives you A and B. Rate laws only have the reactant, so that's why I had to like change my stuff up. Anyway, if the initial concentration of reactant A was 4 molar, I write it like this, and that means 4 molar. You don't write the M in there. Well, raised to the 0 power. What is anything raised to the 0 power, y'all? 1. So guess what? The rate is 2. If the initial concentration of A is 0.0001, guess what? The rate is 2. So the rate of the reaction, if you have a 0 order reactant, is equal to K. Because anything to the 0 power is 1. I'm going to let that soak in. How you feel? So if I double A and I make this 2 times 8 molar, doesn't matter. I still get 2. Okay. So that's for 0 order. And 0 order just means that the exponent, the concentration of the reactant that you're talking about is 0. That's what that means. Good times. So if you look at this, on your Pogel, did you notice how when you plotted the reaction, like it was a curved line? That's either a first or second order. None of the reactions in the Pogel were 0 order. Otherwise, with the 0 order, as you go through the reaction, the rate doesn't slow down. This shows me that as I go through the reaction, the rate slows down. The instantaneous slope of this line gets reduced as time goes on. Let me show you what I mean. Here's the slope of the line as you start. That's a steep slope. That's going fast. That's fast change. Still pretty steep, but less, yeah? Less. And now the slope approaches 0 as the reaction stops or is no longer visible. We'll get to equilibrium. They don't actually stop. Anyway, do you understand the math that I'm talking about? Here, the rate stays the same. It doesn't change based off of the concentration of the reactant. That is what a 0 order looks like. If you're just plotting the molarity. This will be important when we get into the integrated rate laws, which is where calculus comes in and has a party. But I got you. Don't worry about it. It's fine. So everybody's like, I'm never coming back to school. Let's keep K2 because why not, right? Now for first order, that just means that the reaction in, if I have here again, if I have the molarity of A as 3, so 2 times 3 to the first power, what's anything to the first power? Itself, right? So, the rate would then be 6. And there's units to the rate. I'm going to explain to you how to do that. I got a trick for you. Everything's fine. But for right now, the rate is just 6. It does have a unit. We'll get to it, okay? Now, if I double, K stays the same. If I double that to 9, no, that's not double, is it? If I double 3, which is 6, and then I square it, right? 6 squared is 36, times 2 is 72. Did I do that math right? Yeah. face I got is terrified. Anyway, so this is fine. If I double the initial concentration, then I double the rate. I go from 6 to 12. Thank you, Kat. So with first order, whatever you do to the concentration of a reactant, it does to the rate. Double it. If I triple it, right? If I triple this and I get 2 times 9, I would triple the rate. So that's how that works. Still okay? All right. Can you kind of tell them, like, turn up the heat just like a little bit? Like, okay, everything's fine. Now let's get to second order, which is where we square stuff. So second order, this is what I was trying to talk about.
So what does K represent?
K is a rate constant. You'll have to solve for it. We'll get to that. They'll either give it to you or you solve for it, but it's just for every unique reaction, the particles have to hit each other with enough force, they have to hit each other with enough orientation, and when you take all that into account, you get a number that kind of mathematically makes this all work out. Yeah, and so like if the temperature goes up, the K goes up because they're going to be hitting each other more frequently and with more force. So that's kind of what's happening. We'll get into it. I'm so excited. Alright, so let's keep K at 2. So, and let's just go back to having 3, right? And so if the initial concentration of A is 3 molar, and I square it, then I get 18. Can you follow my math there? Cool. Make sure you do exponents first, right? So don't multiply it. Okay. Now, if I double A, so if I go K is still 2, and then this is 6, and it's squared. This is what I was trying to do a minute ago. Now that's 72. So 18 plus 18 is 36. Times 2 again is 72. If you are not real strong at mental math, this is going to be uncomfortable for you. And I'm going to try to help you with that, okay? You'll start seeing the same numbers over and over again. This is not a good time to go to sleep. This is the worst time to go to sleep. Ever. Thank you. I don't want to say any names. I'm going to take. So anyway, if we do some different numbers for K, if the initial concentration is 5, 5 squared is 25 times 2 is 50. I made it up. This does get a little bit easier when you do it in context. So, but if I double it to 10, right, now I have 200. See how that's quadruple when I double it? So when you see that relationship, then you know it's second order in relation to that reactant. That's just how that does. We don't have to do third order and 1.5 order or anything like that. That exists, but we don't have to do it. I promise. I'm sure. Okay. Not really. There's like weird fractional ones. You'll see those more than like larger numbers. They don't really go much above that. I think a 3 is a thing. I'm not super duper sure. But the fractional ones come up sometimes, but I know we don't have to do it. Like, I'm positive. Alright, so anyway, the overall order, what you're going to do, you'll have to do this separately. One for one reactant, you'll have to figure out the order relationship to it, and then a different order for the other one. So if you have 3 reactants, you'd have 3 of these, and then you'd have to figure out the exponent of them individually. So let's just pretend that experimentally I determined the order on A was 2 and the order on B was 1. The overall rate of the reaction would just be 3. Now if the rate in regards to, or the order in regards to B was 1, would this exponent even be there? No. Something without an exponent is to the power of 1. So you do have to be careful of that, right? You're not on your game with math. Yes. Now, if this was again our reaction, and let's say that we determined that the rate or the order for A was actually 0 and this was 2. The overall order would be 2. And guess what the rate law would have? The rate rate law would look like this. Something to the 0 power is 1. So if the order of a reactant is 0, they won't put it in the rate law because it's going to be 1. See? So you got to be careful with that. How do you feel? Stop. Let me slow down for a minute. No, I'm showing you. Before I can show you, I got to tell y'all that. We're not even there yet. We're still like loading the bus. We haven't driven anywhere. That was just a good like math review. So how to do all this? Oh, here's the units for K. Remember how I was like K has units, but I don't want to tell you yet? This looks awful. Do you want to memorize that real quick? Do we tell you the trick I made up? Yeah, let's do it. All right. So look at here. All of this is K, like rate is equal to K and all that stuff. That's the K. Yeah, that looks good. Here's how to do it, okay? Oh, it's still here. All of them had seconds to the -1, which means per second. Do you remember the negative sign was like on the other side of the fraction bar? My dream of becoming a math teacher has come true. I didn't realize it was going to, but it did. Okay, so anyway, what you have to do is all of the rate constants will have, every K will have S -1. It's a rate. So yeah, it has some seconds in there, per second. Okay, so let's start with second order. What you have to do, y'all, is you make M to the second power. Okay, so you write the order as the exponent. This isn't in a book or anything, so if you don't write it down right now, good luck. Write order as an exponent. Subtract 1 and flip the sign or reverse the sign. What would be the best way to do it? Make negative. Whatever. How about multiply times -1? How about that? So let me show you. So for second order, obviously it has the S -1 in there. So what I'm going to do is I'm going to subtract 1. Okay. And then I've got to make it negative. That's how to do. So you subtract, this is the answer for K. There. Subtract 1 and make it negative. Let me show you. Second order, subtract 1, make it negative. Third order, I skipped that one, whatever. But Miss Freeman, we don't have to do second. We don't have to do third order. Yeah, you do. Because if something's first order and second order, the overall reaction is third order. See what I mean? Yeah. What? Yes. Yes. So for third order, I have M, 3 minus 1, -2, 10. Easy? On the chemistry Olympiad, it's a very common question. First order. Watch out with first order because M is 1 minus 1. So M is actually 0. Right? You think that the 0 power goes away? So that's the units on first order. Just S to the -1. What you have to think about with this question is, like, you're trying, the K is going to allow you to cancel all your units so that you're left with molarity per second. And so that's the issue. That's why you're taking 1 away. That 1 is that 1M. So 0 order, 0 minus 1. And then I got to flip that sign around. That's -1, right? So guess what? It's M positive 1. And that positive 1 isn't going to be there. That's not a thing. So it's molarity times seconds -1. trick. Pretty proud of it. Oh, wow. It works. If it was the overall order is 4, it still works. So, anyway, going back to that crazy looking chart that would make you want to cry. If it's 1, do not write it. No, you have to write this. That's the units. It's so, and all these things you're going to be solving for K, and then you'll have to write the unit. And then on the AP exam, they won't give you the credit unless you write the unit. So this is a thing. This is, you and this needs to be friends tonight. Because it's, like I said, it's fine right now, but we're just going to keep adding to this. You have now arrived in AP Chemistry. All right, now, this is where all that was going, right here. So let me talk you through this, okay? All this has to be experimentally determined. The rate law has to be experimentally determined. So they have to give you a chart with experimental data. And it's going to have different trials. And they're all going to be at the same temperature, so they'll all have the same K. How do you feel so far? Don't let this freak you out. They'll also give you the balanced equation. So at the end of this party, this is how I like to do these so I don't screw up. At the end of this party, I need to have rate is equal to K. That's a given. That's always going to be there. And I know that I need to know the order in regards to NO and H2. So I'm going to go hunting through this data to figure out the exponents. So let me show you how to do this. It's actually really easy. So what you have to do, let's look at NO first. To see how the rate is affected by the change in NO, I need to find 2 trials where H2 doesn't change. So these first 2, H2 doesn't change. So I can tell what happens to the rate just off of what happens to NO. So these are the 2. Now, it's better mathematically and mentally to go where it increases. So this doubles. So I'm going to read it this way. As NO's concentration doubles, then think about this like money. This is $2.25. That's $9. How's your math? Watch your decimal places. $2.25 doubled is $4.50, which doubled is $9. So as I doubled this, I quadrupled that. So what is the order in relation to NO? Second. How you feel? Put your 2 here. Now listen to me. There is a really awful, I can barely do it, formula for not eyeballing it. But to get full credit on the AP exam, all you have to do, if they ask you for the order in relation to NO, you have to say when H2 is held constant and the concentration of NO is doubled, the rate is quadrupled, so it is NO is second order. That's all you have to say. Or you can do this really awful formula that I'll show you on the next slide. But I've checked, I'm sure. Look, and I've never not been able to do one in my head. And worst case scenario, you pull out a calculator and be like, that looks like it's times 4. Oh yeah, it is. Okay. So anyway, that is the order of NO is 2. Now, to be able to talk about H2, I have to find where NO is held constant. So in trials 2 and 3, and you would have to say in trials 2 and 3, NO is held constant. And do you remember how I told you that I like to find the one that, don't go this way, read it this way. Okay? So, see how this goes up by half, right? And so, what's half of $1.50, y'all? 75 cents? Does that go by 75 cents? $2.20, look, $1.50, $2.25. Yes. You look at it like money, you get it. If you don't, So, anyway, this goes up by 50%, this goes up by 50%. So, what is the order in relation to H2? Right. Anyway, so that's that. So that's my rate law. So now, all of these have the same K, and this rate, y'all, is that. So if I now, let me see what I have, 0.0900. I need another screen. Does anybody have this open, or y'all just follow along? Let me take a picture. You have it open? Okay, cool. So this rate, what I'm going to do is I'm actually just going to fill this into the formula. I bet I can do it up here. you know what, I'll just erase it. I'll just erase everything. And so if now, y'all saw the rate law, right? It was 2 and then 1. So 0.0900 molarity per second is equal to the concentration of NO, which is 0.20. So I just fill that in. I'm filling, oh, I forgot K, didn't I? My bad. Don't forget K is equal to K times the concentrate. Just pick a trial, it doesn't matter. Just stay consistent with it. 0.20 molar NO, and that was this one second order? Yeah, okay. Second order, and then 0.30, and that was the first order one, so we don't need an exponent there. And so now, to solve for K, you gotta isolate your variable. You're gonna square that, multiply by that, and divide this by that. So how's your math? How's your basic algebra? You're gonna end up having to go 0.900 molarity per second divided by 0.20 squared times 0.30. And that will be your K. My bad. There.
You could use
Easy trial and you'll get the same answer. So I say it real flippantly, like, oh, if you're good at math, you got it. But people make the mistakes on the basic math stuff. And you get 7.5. So K is equal to 7.5. And guess what? What's the overall order of the reaction? Right? 2 plus 1 is 3. So now this is where that little trick comes in. It's definitely got seconds to the negative first. Molarity is 3. Minus 1 is 2. Negative 2. How you feeling? Okay. Huh? Well, that's why I went over the test real quick so you could have time to practice. You're going to have to do your homework every day. Because it's fine when I'm teaching it, but then later, it's not fine. It's not fine later. If you waited to do your homework for the unit for like tonight, like you didn't do any of the chapter 14, you're going to have a busy night. Or a not good quiz grade. All right, so this is how were you feeling me when I just talked you through it? It was all right, right? So if you don't want to think your way through it, basically you fill in the stuff. This is what you do. This is I've never had to do it this way, ever. But here is what you end up getting. There's the rate law. Okay, first order and second order. And then you just plug everything in from one of the trials, which is, this is the one we did. And then this is what I was talking to Christian about. Look, one of the molarity here, if you fill it in, you have 3 M's, 1 M, so you end up with -2, right? Because you subtract. Or actually, no, I'm just kidding. This one cancels and you're left with 2 on the bottom, and then the S is actually on the bottom. So how about you just do what I told you, right? How about that? Or or what I told you. It's not that hard, but when you don't, the thing is sometimes they'll ask you the question and you don't have all the data in front of you. Like you won't have all this in front of you, and they'll say the rate law for this is found to be second order overall, and you wouldn't have any data to be able to find angle and cancel, and you'd have to just know it, and then it would be M minus 1, S minus 1. You don't need it. So sometimes you don't have the data to be able to sit there and cancel. So that's the thing. Anyway, there you go. So this goes back to Beer's law, and let me tell you, on Friday when I went to that workshop, they did a spectroscopy thing with kinetics, and basically you take crystal violet, which is purple, and it turns clear, and so the absorbance goes down over time, and you basically just run 3 trials so you can make a data table and then see if it doubles or halves or whatever, and it's a really big pain in the butt, and so we tried it last year. It's not worth the time with how much we have left to do. So we did a Beer's law lab so you would understand Beer's law. But to me, you're gonna spend 2 days in a lab to get a chart of data so you can sit there and say, okay, it doubles, and it's first order, and that's it. I'm serious. No. So anyway, we already did Beer's law. Remember him? A is the constant for all substances. B is usually a centimeter, and this is concentration, and that's absorptivity. This is absorptivity. That's absorbance. Sorry. Anyway, so you're gonna do 3 trials, and then on the AP exam, they would ask you a question like, why could you not use B? Because you can't use spectroscopy or colorimetry. It's the same with clear things. You'd have to have a colored solution. You want to use red because that's a common color from green. Like this is what we already did. Okay, and so you're gonna do all this stuff. Oh, and they'll give you the path length and everything. And you can just use your Beer's law formula, no problems, and get A. And that A is going to stay the same for all the trials. But look, you're going to do all this, and you're going to do a data table, and here it is. Do all that work to get this. Now, let's look at the order of reaction in regards to all these. So, to find the reaction order for in respect to B, I would have to find 2 trials where C stays the same. So, I'm using trials 1 and 3. So, here's how you would say it. In trials 1 and 3, the concentration of C was held constant while the concentration of B was doubled. While B was doubled, the reaction rate doubled, so B is first order. So the rate law would be rate is equal to K, and then B would be a number 1. Now I have to find 2 trials where B is held constant, and here it is. That's doubled, and this is doubled. So the reaction order in regards to C is also 1. That's the rate law. That's the purpose of that whole lab. Are you sad about not doing that? What? K? What would K equal? To find K, well, and we can do that. Actually, I want you to do that. Find K for me. No, I made, so pick a trial. That's B, that's C, and that's your rate. You do algebra. You can do this. This isn't as scary as it looks. Famous last words. Not so bad, right? You're okay. So you basically end up with 4.2 times 10 to the negative 4th divided by 1 times 10 to the negative 1st, which brings it up to negative 3, divided by 1 times 10 to the negative 1st, which brings it up to negative 2. If you like scientific notation and can do it in your head. It's second order because 1, 2. Subtract 1 away from 2. You get 1. Flip the sign, get negative 1. Second, negative 1. And how does that make you feel? Okay. There is a virtual colorimetry spectroscopy lab for Kinetics. I'm going to try to see if I can get a good write-up for that. That doesn't take me like a super long time. And I might make that like extra credit, especially if you're thinking about taking the AP exam. You're going to have enough homework other than that. But we really, with the amount of acid-base titration lab work, we don't have time for this lab. And that's all there is to it. I hate to say that, but it is. Okay, so you can do all this mess or whatever I just said. Your choice. And so there was the rate law, right? You fill it in for one of the, any of the trials. I just picked the first one. Now, if you're taking the AP exam, and you know how like there'll be a trial and it's all screwy and it's an outlier and it's wrong? So don't pick that trial. How about don't pick that trial, okay? That's the only thing you have to be careful of. This is trial 1. That's the one we did. And then there's your units like I showed you how to do. No problems. And that's it. So go ahead if you want to take the rest of the answer. We're doing all of these. Now let me tell you something. As you're doing your homework, there is one where it comes out to have like an order of 3.5 or 1/2 or something. Don't stress about it. You can kind of see how the numbers are a little bit screwy. Just write down the answer from the answer key, and then you can solve for K like we had done with your calculator, no problems, okay? So don't stress about the specifics of like each math